chapter 13, section 3. It's called counting formulas. It's a little bit more of the same, we're just finding different variations. And the first, so your homework, problems 1 through 5, you're gonna do all of them, and then we're gonna do more where from 6 to 13, you choose any 5 that you like and do those, and from 14 to 19, choose any 3 that you like and do those. And if you wanna calculate how many possible combinations there are for the homework, you're welcome to do that, okay? So, the first type the first type of counting problem we're gonna do is called circular permutations. They're a little bit different, and there's a picture in your book, because a circle doesn't really have a beginning or an end, right? If you were a Girl Scout, I think it's the Daisy song, it says that your friendship is like a circle because it has no end. So, it doesn't matter where you start. What matters is what position you are relevant to other positions, right? So, say these were, and then the whole table turned, but everybody was in the same arrangement, that wouldn't be a new combination, right? Because everybody's still in the same arrangement relative to each other. However, if C and E changed, that would be a new combination, right? So that's what's different about circular problems, is that it doesn't really matter where you start, it just matters who is next to you, basically, who your neighbors are, right? So in example 1, for example, they want to know how many different ways 5 people can be arranged around a circular table. Now, this is not a great circle, but it's an illustration for the example. And they give us a formula, and you are welcome to do all the math in your head and try to figure out why that formula works, or you can just go a little bit lower on the page where it says that in general, for a circular permutation, the number of possible arrangements or the number of permutations is just, okay? So in this case, what's n? 5, there's 5 people, so n minus 1 is 4, so it's 4 factorial. Again, if you don't have the factorial button in your calculator, you just remember that it's 4 times 3 times 2 times 1, and we can actually do that. 4 times 3 is 12, times 2 is 24, times 1 is still 24. So let's see, that's the answer they got for problem 1, okay? So it can begin in any of the 5 seats, which is why you take out basically one of the variables for it. So you just say that instead of using your n, you use your n minus 1. In example 2, they have a lazy Susan. Hopefully you guys know what a lazy Susan is. When I was growing up, I'm an only child and you guys know that, but my best friend Nicole was one of 7 kids. And it actually was just her birthday. When you guys see this, it will have been 2 days ago, because her birthday's April 18th, my birthday's June 18th, we're exactly 2 months apart. Anyway, there was 7 kids, 2 parents, and basically I lived there, so there was 10 people there all the time. They had this huge dining table, and it had a lazy Susan. So the lazy Susan is just the circle thing in the middle of the dining room table so that you can turn it. Instead of passing the mashed potatoes through 10 people, you have a lazy Susan, and the mashed potatoes kind of make their rounds. So Mrs. Larson, in this case, has a lazy Susan in her kitchen. On it she has mustard, I'm just going to count how many there are, okay? Mustard, ketchup, mayonnaise, onions, salt, cheese, pickles, salad dressing. Okay, so that's 8. 1, 2, 3, 4, 5, 7, 8. And we're going to assume that they're covering the whole circle, right? Because theoretically you could put some in here, but that's not a circular permutation at that point, okay? So she wants to know the total number of possible arrangements of these items. Again, it's a circle, so if you turn it one position, you're not changing the arrangement. So there's 8 possibilities. What's n minus 1? So you're going to do 7 factorial. To 7 times 6 times 5 times 4 times 3 times 2 times 1. 42 times 5 is going to be 210, times 4 is going to be 840, times 3 is going to be 2,640, I think, and that's getting way too big. 5,040. That's how many different possibilities there are for these 8 condiments around the lazy Susan. Again, if you don't have the factorial button on your calculator, it's not that hard to type in 7 times 6 times 5 times 4. Make sure you go slow and don't skip one of them, because you will get the wrong answer. Okay? So those are circular permutations. Now, what if you were asked to find, for example, this isn't quite circular, but it's still a permutation, the number of different arrangements of the letters in the word Tennessee. So, not Tennessee Morgan, just Tennessee. Let's see. So first we're going to write out the word Tennessee. And I'm going to write it all caps. And hopefully I did not misspell the name of our state. I did not, okay? So you'd say, okay, 1, 2, 3, 4, 5, 6, 7, 8. That's 8 different letters. So that's going to be I want to figure out how many ways you can combine 8 letters out of 8 letters. So n equals 8. And it's just going to be 8 factorial. Wrong. Why is it wrong? Well, is this E, are they different? No. Is that any different? No. When you're arranging the letters, the E's aren't going to look any different. Right now, if these had little numbers on them, they'd look different, but they don't. They're all E's. So that's going to affect your possible combinations. How many different letters do you actually have? You have T, E, N, S. Those are your 4 different letters. So how are you going to do it? Let's see. The 2 S's, so the total number of arrangements we have, how many objects we have, right? So we have 8 letters, but we only have 4, right, different letters. And the book is going to give us a formula for that. Go to the bottom of page 532 and it says, to find the number of this arrangement, you have to do the number of objects to be arranged, P is the number of these objects that are like, Q is the number of objects that are like, R is the number of objects that are like, and so on and so forth. So, what do we have? T is unique. E, there's 4 that are the same. 4 E's. N, there are 2 N's. What about, that's it only has 1 S, correct? Oh, I misspelled Tennessee, y'all. So it actually has 9 letters, doesn't it? Yep, it has 9 letters. See, I'm teaching y'all math, I'm not teaching geography, not teaching English. 2 S's. So there's 2 S's. Right? Are there any more letters that are repeated? No. So how are we going to solve this? We're going to put n factorial, which is not 8. It's 9. So we're going to have 9 factorial, and then we're going to do it over all the different ones that we have repeated. So 4 factorial to account for the E's, 2 factorial to account for the N's, and 2 factorial to account for the S's. Let's make sure that's what they have. Yes, they have 9 factorial over 4 factorial times 2 factorial times 2 factorial. Now, if you have the factorial button on your calculator, great. If not, you can save yourself a tiny bit of the work by actually writing it out and figuring out what you can eliminate, right? And here you have 4 times 3 times 1 times 2 times 1 times 2 times 1. Okay, so let's just take out all the ones because they don't mean anything. 4, 3, 2. Well, 4, 3, 2. Let's take those out. You could take the 2 times 2 is 4, and you could take that out of the 8, but it's a lot of work. So we're just going to do 9 times 8 times 7 times 6 times 5 over 2 times 2, which we can just say is 4. Okay, so if you don't have the factorial button on your calculator, when you're doing fractions and there's factorial on the top and on the bottom, go ahead and expand it out. So for 3 factorial, write 3 times 2 times 1, so you can cancel out some of the stuff. If you're multiplying that many numbers and dividing by that many numbers, it's just easy to make a mistake. So it's kind of like simplifying, right? You're going to get rid of everything you can. All right, example 3. Let's erase the properly spelled Tennessee. And we'll do example 3. All right, so example 3 says, Mr. Wong keeps 12 books on the mantle for family devotions. So we know that our n is 12. The books consist of 3 identical Bibles. What else is identical? A concordance, a Bible dictionary. I'm not writing these down because there's only one of each of them. 2 copies of a favorite devotional book. So 2, I'm just going to put devotionals. Let's see. A Bible atlas, again, there's just one, and 4 copies of the family's favorite hymnal. So now they want to know, find the number of arrangements possible on the shelf. This is the same as the Tennessee problem. Our n is 12, so we know it's going to be 12 factorial. And then on the bottom, we have to account for all the repeats. That's why I didn't write everything else down, because we don't have to account for it. So we have to do 4 factorial times 3 factorial times 2 factorial. And notice I just wrote them from biggest to smallest. So let's expand those out. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Then we're going to do it over 4 times 3 times 3 times 2. Again, let's cross out all the ones. And then we have 4, 3, and 2. We can cross them out from here. And actually, I think we can probably cross out a little bit more, because notice 3 times 2 is 6 times 2 is 12. So we have left 11, 9 times 8 times 7 times 5. Nothing on the bottom. And that should give you an answer of 1,663,200. That's how many ways there are to arrange those books. Okay, but same concept as we had before. Now, so we're going to talk about 2 more final types of counting. It's mutually exclusive sets. Actually, looks like it's just going to be 1. So it says 2, but we're only going to do 1, which is mutually exclusive. Now let's look at the example that they're talking about. This isn't an example, like it doesn't say example 4, but on the bottom of page 533, it says, I'm going to probably want to write all this down. There's a choir, and it has 22 sopranos. I'm just going to write the first 3 letters. 24 altos. 25 tenors. And 17 basses. Okay, so those are all the members of this choir. Now it says, how large is the choir? It says, this part's easy, don't worry. They're telling you what positions they sing, right? These are all the positions in the choir, so you just add them up. 6 and 5 is 11, 18, carry the 1, 2, 4, 6, 8. Should be 88 people in the choir. Let's see if we're right. Yes. Now, what if there's also a 55-piece orchestra? I'm writing it over here and you'll see why in a minute. And in that orchestra, there are 12 of the choir members. Which means 12 of the positions from here are basically serving a dual purpose, okay? So, if there are all of the how many will participate in a combined program? So this time, if we just add the 88 plus the 55, that means that these 12 are going to get included as part of the 55 and as part of the 88. So we're going to get the incorrect answer. So how do we do it? In this case, you just have to subtract it. So it's really easy. You have 88, let's add the 55, so you get 13, 6, 8 is 143, but we remember that 12 of them got duplicated basically, so we just subtract one set of 12 from here. So there's 131 people total in the orchestra. That was a simple problem. Sometimes it's going to get a little more complicated, right? Now, sometimes you have mutually exclusive sets, which means that if somebody participates in one of these, they can't participate in one of these. So it's a little bit different from that, except I don't think, so it's just sets whose intersection is empty. I'm trying to think. Yeah, they're not gonna, so it only affects the counting formulas if you go to page 534. Now, you can have permutations like we've done before, which is how many possible combinations do we have for m and n, right? And in that case, you just add them together, basically. That's the fundamental principle of counting. You multiply m times n, you got your answer. How about m or n event occurs? Then you add them together. But what if you want m to occur, but not n to occur, okay? So only one of them occurs. That's what's called mutually exclusive, which is kind of what this is. You're having the 12 people, actually this is inclusive, right? You're having the 12 people occur in one and in the other. Well, what if you have something where you want one event to happen? So what is the possibility that either, that doesn't help, a dice which has 6 sides, what's the possibility that it's going to land on either a 4 or a 6? So that's a little bit different, right? You can have, what is the possibility that it lands first on a 6, then on a 4? Or you can say, well, honestly, I just want it to land on a 6 or a 4. I don't care which one of the two it lands. In that case, you're going to do one of the numbers, which is event 1, plus the second number, but then you're going to subtract this, which is going to be what's the same, right? In this case, you're saying how many people are going to be in the orchestra or in the choir. Well, it's these guys are going to be in the orchestra, these guys are going to be in the choir. However, these guys are going to be in both, so they're not going to be in one or the other, they're going to be in both of them. You have to subtract it, which is P. You can use whatever letters you want, but basically this is one event, this is the other event, and that's kind of what's mutually exclusive. You can't, if you're counting them here, you can't count them here, right? A person can't be in the same place 2 times. They're in the place once and they're doing 2 things, kind of, okay? Now, if you go to page 534, on the very top, it gives you basically all the formulas we've gone over, right? The principle of counting, mutually exclusive events, inclusive events, kind of, which is what we just went over with the orchestra, permutations, combinations, circular permutations, which we did at the beginning of this section, and then the permutations with indistinguishable objects, which is just a fancy way of saying objects that repeat. So like in Tennessee, you had letters that repeated. In the books, you had extra copies of the same books. So that's what it means by indistinguishable items, okay? So for your exercises in problems 1 through 6, you're gonna figure out how many ways the letters can be arranged. Now they're not all gonna use the same formula because some of those words don't have repeating letters and some of them have 1 repeating letter, some of them have 2. So write down the word like we did Tennessee, write it all capital, and look for what letters are unique and what letters are not. And then in the problems 6 through 19, it's gonna be any of the counting formulas that we've talked about, okay? So you're just gonna read the problem, try to figure out what they're looking for, whether it's exclusive, whether it's not exclusive, whether it's a permutation, whether it's different combinations. So just look and see basically, all of them should fit into one of the formulas that's on the very top of page 534. So read the problem and try to figure out which of those formulas is gonna apply. And because I know it's a little complicated and sometimes it's hard to figure out what the right formula is, that's why I'm letting you guys pick. So if one of the problems you just really can't figure out which formula to use, don't pick that problem. Pick one where you know for sure what type of formula you're gonna use. Okay, that's it. Next class we'll be going over the